Welcome to the Depth Dive. We're all about getting to the core of complex subjects. Have you ever, grappled with a topic where you feel like you can follow the rules, maybe the formulas, but you just haven't quite got that intuitive feel for it, that deeper sense of understanding? It's a common thing, right? Especially when things get really intricate underneath. Well, today we're diving right into that. We're looking at how some really profound ideas in physics are actually understood, not just mathematically, but intuitively. And we'll explore how a pretty revolutionary mathematical language helps bridge that gap. We're drawing from a classic text that breaks these concepts down brilliantly.
That's exactly right. Our mission today is really to pull out the key ideas about truly understanding physics. And as a part of that, introduce you to this incredibly powerful tool, the differential calculus of vector fields. We want to show you how this elegant language simplifies things, clarifies fundamental laws, and makes complex physics maybe a bit more accessible and definitely more intuitive.
Okay, so let's start there. How do physicists actually tackle those real-world problems that seem so complicated? Our source points out right at the start that just directly solving the differential equations can be, well, really difficult. So what's the approach? Is it just grinding through the math?
No, it's definitely a dual approach. It has to be. On one side, you've got the precise differential equations. These are, fundamental. As far as we know, they're exact. The source actually says if you learn these, there's nothing to unlearn. They are the only precise way of presenting the laws. You need them. But then there's this other crucial path using what are called heuristic models.
Heuristic models? Like what?
Think of things like field lines or concepts like capacitance, resistance, inductance. They're described as very useful. They help you get a very good idea of the behavior of a system. They let you develop that feel for what should happen in a situation. Now, the text is clear. These models are not really adequate and accurate for all situations, but they build that essential intuitive foundation.
Which brings up something fascinating. The source mentions this difference between a purely mathematical understanding and a physical understanding. It says that just knowing the math of, say, Maxwell's equations isn't really enough for a physicist, that mathematicians focusing only on the math can actually be led astray and often make little contribution to physics. That's quite a statement.
It is, isn't it? And it really highlights Dirac's definition of understanding an equation. It's quite profound. He basically said, I understand what an equation means if I have a way of figuring out the characteristics of its solution without actually solving it.
Without solving it.
Yeah.
Wow.
Yeah. So if you can grasp the behavior, predict what should happen under different conditions without needing to calculate every single time, then you understand it. This physical intuition, it's described as completely unmathematical, imprecise, and inexact, but crucially, absolutely necessary for a physicist. So the approach in our source material is very deliberate. Start with the complete fundamental laws first, get those down, then sort of step back and apply them to simple situations and develop the physical ideas as you go.
Instead of building up historically or experimentally.
Exactly. That would just take too long. This way is more efficient for learning the core concepts quickly.
Okay, that philosophical underpinning is really helpful. So let's get into this crucial mathematical language that enables that deeper understanding. Before we tackle the big laws, we need to get this idea of fields. What exactly are we talking about here?
Right. Simply put, a field is just some quantity that depends on position in the space. It varies from place to place. And we generally talk about two main types. First, a scalar field. This is where at every single point in space, you just have a number, a single value, a scalar. Think about temperature in a room or maybe in a block of metal that's being heated. At any point, there's just one temperature.
Okay, like a weather map showing temperatures.
Exactly. And we often visualize these using isothermal surfaces connecting all points that have the same temperature, like contour lines on a topographical map, but for temperature.
Got it. And the other type?
That would be vector fields. Here, at each point in space, you don't just have a number, you have a vector.
Meaning magnitude and direction.
Precisely. Magnitude and direction at every point. Good examples would be, say, the velocity of water flowing in a pipe, or wind speed and direction, or sticking with our heated block, the flow of heat itself. We could represent this by a vector, let's call it h. At every point, heat is flowing with a certain intensity, that's the magnitude, and in a specific direction.
And how is 8 defined exactly?
Well, its magnitude is the thermal energy flowing per unit time, per unit area, through a tiny surface element that's oriented perpendicular to the flow direction. And its direction is simply the direction the heat is flowing. What's useful is that if you want the heat flow through any little surface element, one with the unit normal vector n, You just take the dot product, HDN.
Okay, clear distinction. Scalar fields are just numbers everywhere. Vector fields are arrows everywhere. Now, if these fields vary across space, how do we describe that mathematically? How do you take a derivative with respect to position? I mean, you could do x or dec, but that feels incomplete, somehow dependent on your axis.
You've hit the nail on the head. That's the core challenge. Those individual partial derivatives like dex, they do change if you rotate your coordinate system. They aren't intrinsically meaningful on their own in that sense. But here's the clever part, the trick physics discovered. If you take the collection of all three partial derivatives, tex and ches and tes, that collection does behave like a vector.
So the combination is coordinate independent, even if the parts aren't.
Exactly. It works because the temperature difference between two nearby points is a scalar. It doesn't depend on how you set up your axis. And you can write AT as tes and t's. Since 8 is a scalar and the displacement is a vector, the partial derivatives must be the components of a vector for this equation to hold true in all coordinate systems.
And this vector formed by the partial derivatives, this is where the famous DIL operator, or nobla, the upside-down triangle, comes in.
Precisely. We define the gradient of t, written ATT or sometimes grad t, as this very vector. Tex, ticons. Physically, what AT represents is the spatial rate of change of t, how t changes as you move through space. And here's the key insight. The direction of the vector t is the direction in which t increases the fastest.
The steepest uphill slope.
Exactly. It points straight up the steepest slope on your temperature hill, if you like, and its magnitude tells you how steep that slope is.
That's a really powerful, intuitive way to think about spatial change for scalars. Okay, but what else can we do with this edge operator? It feels like it should combine with vector fields too, right? Like dot products or cross products.
Absolutely. But first, a quick reminder, edder's an operator. It's, as the source says, hungry for something to differentiate.
Right, it needs to act on something.
Yes, and the order matters. Edge doesn't mean much, but edge t is the result, the gradient vector.
Yeah.
So when we combine with a vector field, let's stick with our heat flow vector edge. There are two more crucial operations that pop up everywhere in physics. First is the divergence. We write it as edge, using the dot product symbol, or sometimes div edge.
Dot product, so the result should be a scalar.
Exactly right. It results in a scalar field. At each point, you get a single number, calculated by adding the partial derivatives of the components. Ednant plus edge plus edge. Now, the physical meaning of divergence is super important. It relates to sources and sinks of the field, but that's maybe a deeper dive for another day. For now, just know it's an edge dotted with edge.
Okay, divergence is he gives a scalar. What's the other one?
The other is the curl, written EE using the cross product symbol, or curl edge.
Cross product. So that should give us a vector.
You got it. The curl produces a vector field. Its components are a bit more complicated, involving derivatives across different axes. For instance, the x component of the curl is EE. It involves how the I component changes in the z direction and how the z component changes in the e direction.
Okay, that looks more complex.
It describes the rotation or circulation of the vector field at a point. Again, the deep physical meaning is fascinating, but we'll park that for now.
So just to recap the operations with each, we have key, the gradient of a scalar, which gives a vector. Then we have EE, the divergence of a vector, giving a scalar. And ECE, the curl of a vector, giving another vector.
That's the set. Those three operations are fundamental.
And the beauty, as the source emphasizes, is that these allow expressing spatial variations in a convenient way, in a way that is general, in that it doesn't depend on any particular set of axes.
That coordinate independence is the key. It elevates the description beyond arbitrary choices. And this leads us directly to one of the most elegant applications, Maxwell's equations.
The cornerstone of electromagnetism.
Exactly. Using this Airchen notation, the complete classical theory of electricity and magnetism can be written down in just 4 equations. They take on an elegantly simple form. You have AGE, that relates the divergence of the electric field E to the charge density, arrows B. The curl of E is related to the changing magnetic field B. Then arrows B equals 7. The divergence of the magnetic field is always 0, no magnetic monopolars. And finally, C's B 0 plus Joyer, the curl of B is related to the changing electric field and the electric current density J.
Just those 4. That's incredible. Char is charge density and J is current density.
Yeah, is charge per unit volume, J is charge flow rate per unit area. Everything about classical E&M is packed into those equations, thanks to the Airchen notation.
It really highlights the power of this language. Can we see it in action in a slightly simpler context, maybe? Just to get a feel for how it clarifies things?
Sure, let's go back to heat flow. It's a great example. Remember the simple case for a slab of material. Heat flow J is proportional to area A, temperature difference, T2, T1, and inversely proportional to thickness dJ, values T2, T1 aid, where key is thermal conductivity.
Right, the basic lab experiment version.
Exactly. Now, how do you handle heat flow in some complicated, weirdly shaped object? You can't easily define D or A everywhere. This is where the gradient comes in beautifully. We can express the local heat flow vector H directly using the temperature gradient HT. The relationship turns out to be remarkably simple. HT.
Okay, so the heat flow vector HE is just proportional to the temperature gradient, HT.
That's it. And notice the minus sign.
Right, you mentioned that. Heat flows from hot to cold.
Exactly. KHT points uphill in temperature towards hotter regions, so H needs that minus sign to point downhill towards colder regions, which is the direction heat actually flows. And this equation, HT, is a proper vector equation. As the source says, it shows the physical content most clearly, without reference to any arbitrarily chosen coordinate system.
It boils the complex situation down to a fundamental local relationship. I see the power now. What happens if we apply twice? Take second derivatives. Are there more elegant connections hidden there?
Oh, absolutely. And there are some really neat results. In fact, two specific combinations of second derivatives using A always give zero, which is quite elegant.
Always zero? Which ones?
First, if you take the curl of the gradient of any scalar field T, you get zero. So HTT, 0, 0. Always.
Why is that intuitively?
Well, think of HT as just pointing straight up the hill. There's no swirl or curl in that kind of field. It's like trying to calculate AHA for vector A, which is always 0. The gradient vector is, in a sense, aligned with the operator in the curl.
Okay, curl of a gradient is 0. What's the other one?
The other is the divergence of the curl of any vector field H. That's also always 0. Perhaps EH equals 0.
So if a field has curl or circulation, its divergence is 0.
Exactly. Think of water swirling in a drain. If the water isn't compressible, then the amount flowing into any tiny region has to equal the amount flowing out. There's circulation, but no net divergence, no source or sink right there. It's analogous to AEB being 0 in vector algebra.
Those 0 results seem really fundamental. Do they lead anywhere?
They lead to some very important mathematical theorems, which we won't prove here, but are crucial in physics. Basically, if a vector field A has 0 curl, then it must be expressible as the gradient of some scalar field, eta, like electric fields in static situations. And if a vector field D has 0 divergence, then it must get the curl of some other vector field, DHEC, like the magnetic field B. These are really powerful consequences.
Wow, okay, so those are the combinations that give 0. What about the ones that don't give 0? Is there a standard second derivative?
Yes, there is. The main one is when you take the divergence of the gradient. T. This is not generally 0. This combination gets its own special name and symbol, the Laplacian operator, written as dabla squared.
Yep, apla. And in rectangular coordinates, it's simply the sum of the second partial derivatives. T plus 0 plus L over Pater plus O rho plus gives you another scalar field. The operator itself is a scalar operator, and it shows up all the time in physics, wave equation, diffusion equation, Schrödinger equation.
So it's a really fundamental operator.
Absolutely. And you can also apply it to a vector field, component by component, in rectangular coordinates.
And are there other non-zero second derivative combinations? The main other one to know is the curl of the curl. This one doesn't vanish, but there's a useful vector identity that lets you rewrite it. It turns out cancel EH is equal to HA. So you can break it down into operations we already know. A gradient of a divergence minus the Laplacian acting on the vector.
Okay, so there's a whole algebra for how these add-change operations combine.
Exactly. It's a very powerful mathematical toolkit.
With all this power, though, are there any tricky bits, common mistakes or misunderstandings people run into when using this algebra? Any pitfalls?
Yes. The source highlights two important ones to be aware of. Pitfalls, as it calls them. The first one is about remembering Yage as an operator. You might see an expression like HA, and Fauci are two different scalar functions.
Right, the gradient of psi crossed with the gradient of phi.
Yeah, and you might think, hey, it looks like AA, that should be 0, because both terms start with H.
But it's not 0.
Generally, no. And the reason is subtle. Even though both use the Thurnus symbol, they are acting on different functions, phi and phi. This means the resulting vectors, and shunted phi, are the gradients of two different scalar fields. They won't necessarily be parallel, so their cross product usually isn't zero.
Ah, because the thing being differentiated is different in each case.
Exactly. It's not the same situation as Yen-Shunnett, where both AND operations are tied to the same function. That one is always zero, as we said. But Kerif is different.
Okay, that's a subtle but important distinction. Operator context matters. What's the second pitfall?
The second pitfall involves coordinate systems. All these rules and definitions, especially for divergence, curl, and the Laplacian, are expressed most simply in standard rectangular Cartesian coordinates, x, y, z.
What happens if you use, say, polar coordinates or spherical coordinates?
You can express these operations in other coordinate systems, but the formulas become much more complicated. And applying them component by component gets tricky. For instance, if you try to calculate the Laplacian tech acting on a vector field by just applying the scalar Laplacian formula to the polar components, like the radial component, you get the wrong answer.
Why?
Because in polar coordinates, the direction of the unit vectors, like the radial direction vector, changes from point to point. The simple formula doesn't account for that change in the basis vector's directions.
Ouch. So it's easy to make mistakes.
Very easy. The source basically advises that it's usually safest and simplest just to stick to rectangular coordinates and avoid trouble, especially when operating on vectors. While the scalar operator tach can be written correctly in any system, applying it to vector components in non-rectangular systems requires extra care, or using the fundamental coordinate-free definitions. Stick to rectangular for calculations unless you really know what you're doing.
That's very practical advice. Okay, so we've taken quite a journey here. We started with this idea of needing more than just math for physical understanding, needing that intuition. Then we dove into the language that helps build that intuition and express the laws elegantly, fields, and especially the Riemann operator with its gradient, divergence, and curl. We saw how it massively simplifies things like Maxwell's equations and the heat flow equation, stripping away the dependence on arbitrary coordinate axes.
And that really is the core value. It's not just about neatness, although it is neat. This notation, as the source puts it, shows most clearly the physical content of the equations without reference to any arbitrarily chosen coordinate system. It gets you closer to the underlying physics itself. That's the real power.
So let's leave our listeners with this thought, going back to Dirac's definition of understanding an equation. That idea of having a way of figuring out the characteristics of its solution without actually solving it. How might applying that mindset seeking to grasp the essence, the behavior, without just relying on brute force calculation, how might that change your approach to complex challenges in your own field, whatever that might be? It feels like a universally useful idea, not just for physics.
Definitely something to chew on.
Keep exploring, keep asking questions, and keep diving deep into the subjects that fascinate you. Thanks for joining us on The Deep Dive.